Hello everybody and welcome to our next video in Unit 3, which we're going to talk a little bit about solids, talk a little bit about gases, but more so we are going to talk about gases and review some of those gas laws that we had talked about in Chem 1. So before we get into the gases, of course, let's go ahead and start off a little bit more simple, right? At least for this unit or for this section of the notes. So for solids, okay, solids can take on two different forms. Solids can be either crystalline in nature, which means that they're highly organized three-dimensional structures. So something like this. You'll see that each of these particles, when they have their intermolecular forces or their intramolecular forces, if it's an ionic bond, they form very, very organized structures. And we typically call that a crystalline solid. Or solids can also be amorphous. Amorphous. And amorphous means that they don't really have an orderly arrangement. So a good example of an amorphous solid would be like silly putty, like Play-Doh, something like that. You'll notice that the bond lengths in between them are kind of all different distances. It's not entirely a very orderly arrangement. We don't necessarily study amorphous solids all too much because there's a lot better chemistry in the crystalline solid section that we at least talk about in AP chemistry. Another example too would be like rubbers. Rubbers are amorphous solids. We have different types of waxes. And different plastics can also be amorphous plastics. And of course, the particles in the solid state of matter have only vibrational energy. All of the particles in the solid state of matter, all they can do is vibrate back and forth, which is exactly what happens here. That's why the particles retain their shape, is because they can't slide past one another very easily. So they're able to retain the shape that they have. Liquids, on the other hand, liquids are interesting because these are the smallest class of matter. I feel like we tend to think that there's a lot of liquids because most things that are liquid have water as the solute, and water, of course, water as the solvent, I'm sorry. And of course, we know that water is the universal solvent. It dissolves most things because it is a highly polar molecule. So because of that, most things that we are familiar with that are liquids have water in them. But overall, liquids are the smallest class of matter. It's very unlikely for a lot of particles to exist as a liquid. At our conditions of pressure and temperature, most things will exist either as a gas or as a solid. And atoms in the liquid phase of matter have a vibrational energy, and they also have translational energy. And translational energy means that the particles could slide past one another very easily, which is why they take the shape of the container that they're in, because those particles could slide past one another. So depending on whatever type of container you have a liquid sample in, it takes the shape of that container. Liquid particles are packed very tightly, but they're not as tightly as solids. And that's because liquids and solids take up similar volumes due to their inability to be compressed. So I can't take a liquid and make it take up any less space than a solid in the same vein as a solid. And that's because the particles of solids and liquids are already very, very, very close together. Liquids are only a tiny bit farther apart than solids are. Of course, the exception to that is water. Water is the only material that in the liquid phase actually contracts a little bit. But yeah, they take up, we cannot compress liquids or solids because they're already very tightly packed to one another. Movement and arrangement of liquids is influenced by temperature. So we've already been talking about how the temperature of a sample is a measure of its kinetic energy, right? And that's what that next statement is saying there. Higher temperature means more kinetic energy of the particles, as well as intermolecular forces. Intermolecular forces. So if two particles have very high forces of attraction to one another, because they have stronger intermolecular forces between them, they don't slide past one another as easily. And therefore, they might be a very viscous material. So a great example of that is like glycerin, right? If you're familiar with glycerin, it's very, very thick, right? Very, very viscous, or like honey, for example. Those particles are very attracted to one another. So as a result, they're not going to flow as easily. So if we want, we can make a little note here. If something is very viscous, that means that it cannot flow very easily. So a good example is like honey, or you might see like molasses. Doesn't flow either. And the last one, of course, which we're going to focus most on this video, are gases. So gases, of course, take up the most amount of space, and that's because they have the most amount of energy. Atoms have vibrational, translational, and rotational energy. So not only do particles of a gas vibrate back and forth, not only can they slide past one another very easily, but they can also rotate off of the surface of the liquid. So gases are able to do that because they have so much energy. And in fact, we add that rotational energy there. That's what makes a gas a gas. And gases have an undefined shape and volume. So gases will take up the space, the whole entire space of a container, because those particles have so much energy, and they want to be very far apart relative to their size. We can also change the volume of a gas because we can force those gas particles close to one another. And if we compress them so that they are close, of course, we increase the pressure. So that's a very good Boyle's law relationship. When we increase the pressure, we decrease the volume. The space between the gaseous particles are about 4,000 times larger than the spaces between the liquids and solids. So just imagine that a liquid and solid particles are that far apart. Gaseous particles are 4,000 times farther apart than those. That's huge. I mean, if we think about it, that's even farther than from here to here, right? Super far apart relative to their size. And gas particles don't like to be near each other because they have all of that energy. And of course, in Chem 2, we talked about phase diagrams. We don't have to talk about phase diagrams for us, but I do like to bring it up here because it does show how pressure and temperature affects the state of matter of anything, really. So if you are in Chem 2 right now, that's okay, because we're going to get to this eventually. College Board does not assess you on phase diagrams, but I just like to bring it up. Typically, you have like a V or a Y shape in here, and it goes SLG. So I like to remember slug. So here's the solid portion of the phase diagram. Here's the liquid portion, and here's the gaseous portion. And you'll see that on my axes here, on my y-axis is pressure, and on my x-axis is temperature. So as the pressure and temperature changes, we can actually go between different phases of matter. So for this particular substance, if I have a relatively high pressure and a low temperature, this particular sample would exist as a solid, right, at a high pressure, but at a very low temperature. On the other hand, if I have that same exact substance, let's say I decrease the pressure, but I increase the temperature, that will change that particular substance to a gas. So all depending on that pressure and that temperature we can change that particular state of matter. Anywhere along each of these lines, we can also have two states of matter that coexist in equilibrium, is what that's called. So if I happen to be right on this portion, whatever that particular pressure or temperature will be, I would have both a solid and a liquid that coexist. Here, if I'm at those conditions of pressure and temperature, I would have a liquid and a gas that coexists. If I'm right here, that's called our triple point. This is where all three phases of matter coexist, which is really cool, actually. There is a lab with carbon dioxide that we can do that. I just have a problem because I don't know how to get carbon dioxide, dry ice, and I don't know how to transport dry ice. Would be a cool lab if I probably could if I thought a little bit harder about it. But anyway, that's a cool lab. We can see all three states of matter for CO2 at a very specific pressure and temperature for that. This brings us to Avogadro's law. So Avogadro's law is a really good example of how the volume of a gas changes proportionally with the number of moles of the gas as long as we're at the same temperature and pressure. So Avogadro's law says that equal volumes of gases at the same temperature and pressure contain equal numbers of particles. And notice how it just says the same temperature and pressure. This doesn't have to be at STP. All that matters is that it's at the same temperature and pressure. So because they have the same number of particles, they would occupy the same exact volume. So if I consider, in this case, these three balloons, all of these balloons have the same number of particles. And although there's not 6.02 times 10 to the 23rd of whatever inside of those, it's just a nice sample of them. So let's count the particles. Looks like I have 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's count this one. 1, 2, 3, 4, 5, 6, 7, 8, 9. And in this last one, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're going to imagine that in this scenario, 1 mole is equal to 9, right? So all three of these balloons have the exact same number of particles. So we'll write here, these have the same number of particles, right? So if it was 1 mole, let's say, all of these would contain 6.02 times 10 to the 23rd particles. Because each of these are at the same temperature and pressure, so if I have these 3 balloons with these 3 different gases, if these are at the same temperature and pressure, all 3 of these, regardless of the identity of the gas, would occupy the same exact volume. I thought I had cut something off there. I was looking at that. I was like, am I missing something? And I am. That's an important piece of information. These would occupy the same exact volume. So this balloon is the exact same size as this balloon, which is the exact same size as this balloon. All of these have the same number of particles, and therefore they occupy the same volume. So of course, if this has 9 particles in it, right, it would occupy some volume. But for chemists, we never work on a 9-molecule scale. We tend to work on a molar scale. So if I were to have 1 mole of each of these substances, 1 mole of helium, 1 mole of ammonia, 1 mole of oxygen, regardless of the identity of each of those and their molar mass, they all would occupy 22.4 liters of a gas at STP. So I don't have this in the notes, so we're going to make a little note here. But Avogadro's law says that at the same temperature and pressure, the same number of moles would contain the same volume. So the number of moles, so I'll put a little note here, number of moles and the volume is proportional. So of course, if my number of moles goes up by 2, the volume would also go up by 2. But we also have the standard molar volume of a gas. So in this case, at STP, 1 mole of any gas occupies a volume of 22.4 liters. Okay, that's important. This right here is super important, as is this. And we're going to work with both of these in the next couple of sample problems together. So rather than talk more about that, let's just go ahead and dive in. We actually don't even need that much space to do this, because this is a great example of Avogadro's law and putting it to use just by looking at a balanced chemical equation. So it says, consider the reaction below, assuming that temperature is held constant. That's important. Temperature is held constant right here. How many liters of hydrogen would be needed to fully react with 2 liters of nitrogen? So let's say in this first balloon, I have 2 liters of nitrogen. I want to know how many liters of hydrogen at the same temperature and pressure would be needed to react with that. If I look at the balanced chemical equation, it looks like 1 mole of ammonia reacts with 3 moles of hydrogen. So we could also say 1 volume of nitrogen reacts with 3 volumes of hydrogen to produce, not 4, 2 volumes of ammonia, whatever the volume is. In this case, we're going to say 1 volume is 2 liters. So if I react 2 liters of nitrogen, how many liters of hydrogen would react with that? Looks like 3 times because of the balanced chemical equation. So my answer is 6 liters. You don't have to do any complex or sophisticated math to figure this out. It's just a ratio using that balanced chemical equation. How many milliliters of ammonia would be formed? So we're going to figure this out here. If 15 milliliters of nitrogen reacts completely. So in this case, I'm going to set my 1 volume equal to 15 milliliters. Looks like I would produce double the volume of ammonia. So my answer should be 30 milliliters. This is a weird unit for volume, but it works, right? I mean, don't let the units get in the way. It's still a unit of volume. How many meters cubed of hydrogen would be needed to produce 30 meters cubed of ammonia? This one's a little bit weird because it's not as straightforward. So I have a 3 to 2. Oops, didn't mean to do that. I have a 3 to 2 mole ratio here. So what I like to do is I'm just going to get it to equal 1 in this case. So if I think about this, if this is 2 volumes, I would consider 1 volume to be 15 meters cubed. So if 1 volume is 15 meters cubed, I would times that by 3, and I would get 45 meters cubed. So then it says how many volumes of both nitrogen and hydrogen are needed to produce 12 volumes of ammonia. So here's 12 volumes. Again, in this case, it's not even giving me any units. It's just 12 volumes. So if I look at this balanced equation, if this coefficient is 2, I'm going to divide it. So I find that 1 volume is equal to 6. Okay. And then let's use our balanced chemical equation. If 1 volume is equal to 6, looks like I would have 6 volumes of N2. And 6 times 3 is 18 volumes of hydrogen. Not rocket science here. Okay, I think this one's actually a pretty easy gas law to really conceptually think about because it is so easy. You're just using that balanced chemical equation. This, however, is only true when temperature and pressure is constant. So it technically should have said that in this problem, temperature and pressure. If they changes, we have a whole new world of stuff to do, which you won't have one of those problems, not on your AP exam exactly, but maybe for me, I don't know. I really don't think I ask those types of questions. But this is as simple as it gets for Avogadro's law in this example. The next question says a sample of nitrogen gas has a volume of 1.75 liters at STP. How many moles of nitrogen are present? So I'm going to start off with 1.75 liters, and this is at STP. So we know that our standard molar volume of a gas says that there are 22.4 liters of a gas that's equivalent to 1 mole of that gas. Any gas at STP occupies a volume of 22.4 liters. So all I have to do is just divide those two values, and I would find that this is equal to 0.0781 moles of nitrogen. And there's our answer. So very simple. We can only use the 22.4, however, at STP. This is only good at STP. And that's because if I have other conditions for pressure and temperature, the volume will not be that, because of course it's affected depending on whether the temperature or pressure is higher or lower. Let's try the next one. Kind of put some stoichiometry and gas laws together in one. So quicklime is produced by the thermal decomposition of calcium carbonate, which is CaCO3. Calculate the volume of CO2 at STP. So I want to know what's the volume at STP that's produced from the decomposition of 152 grams of calcium carbonate by the reaction below. So I'm going to start off with 152 grams of calcium carbonate. And because I'm in units of grams, notice this is a solid, so you can use solids, the molar mass for solids. We can't use 22.4 because this is not a gas. 22.4 liters per mole is only used for gases at STP. Let's convert this to moles by finding the molar mass for calcium carbonate, which is 100.09 grams is equal to 1 mole. We'll look at that mole ratio. Looks like it's a 1-to-1 mole ratio. This is already balanced. 1 mole of calcium carbonate produces 1 mole of CO2. Now, CO2 is our gas, and because we're assuming that this is at STP, we can do a conversion directly from moles of CO2 to liters of CO2, because 1 mole of any gas occupies a space of 22.4 liters. And if I solve for that, I get 34 liters of CO2. This should be 34.0. Let me erase that and do it again. That looks quite sloppy. I couldn't use Avogadro's law here because my starting reagent was a solid. So because that is a solid, I can't do that simple mole volume relationship here. So just to be careful, you can only really use that Avogadro's law if you are going from your volumes of 2 reactants or products or combination of those. Otherwise, you'd have to use stoichiometry for solids and liquids. Let's take a look at 10 here. Oh, this is a good one. So 10 says a sample of methane gas having a volume of 2.80 liters at 25 degrees Celsius and 1.65 atmospheres was mixed with a sample of oxygen gas having a volume of 35 liters at 31 degrees Celsius and 1.25 atmospheres. The mixture was then ignited to form carbon dioxide and water. Calculate the volume of CO2 formed at a pressure of 2.50 atmospheres and a temperature of 125 degrees Celsius. This is a packed question. Okay, it might not seem that packed, but there's a lot of stuff going on, a lot of numbers. First things first, like I always tell you, write an equation down. Let's see how neatly I can do this. So methane gas. I like to actually take all this information and I write an equation with my numbers underneath. So you kind of know what I'm talking about here. Reacting with oxygen. And it forms carbon dioxide and water. So a really nice combustion reaction here. Let's balance this. Looks like I need a 2 and a 2. Let's write some of these numbers here. So a sample of methane gas having a volume of 2.80 liters at 25 degrees Celsius at 1.65 atmospheres was mixed with a sample of oxygen gas having a volume of 35.0 liters at 31 degrees Celsius and 1.25 atmospheres. We want to know what volume of CO2 is produced at a volume of 2.50 atmospheres and a temperature of 125 degrees Celsius. Woo! That's a lot. Okay. This question isn't explicitly stating this, but this is a limiting and excess reagent problem. It is not telling you which of those reactants, methane or oxygen, is your limiting reagent. So you have to figure that out before anything. What's the limiting reagent? Because that's going to determine how much CO2 can be produced. How do I know what the limiting reagent is? Well, how do I find the number of moles giving all of those conditions, right? So I have the volume for both reactants. I have the temperature of both reactants, and I have the pressure of both reactants. We can find the number of moles that's reacting using PV equals nRT. So we're going to use PV equals nRT first to compare the number of moles of methane that reacts with the number of moles of oxygen. So let's use PV equals nRT to solve for N, the number of moles. Pressure is 1.65 atmospheres. Volume is 2.80 liters. Let's solve for N. It's 0.08206. Temperature, so 25 plus 273 gives me 298 Kelvin. And when I solve for that, you should get 0.189, and that is moles of methane. So at those conditions, we would have input 0.189 moles of methane. So based on that, how many moles of CO2 could be produced? Let's look at the balanced chemical equation. 1 mole of CH4 produces 1 mole of CO2. So if I have 0.189 moles of CH4, that means I could produce 0.189 moles of CO2. Same number. Let's compare that to oxygen here. So I have O2. We're going to use PV equals nRT again. So I'll write PV equals nRT. Pressure for oxygen is 1.25 atmospheres. Volume is 35 liters. I'm going to solve for N. There's R, and temperature in Kelvin is 304. And if I solve for N here, my number of moles is 1.75 moles of O2. So I would have input 1.75 moles of oxygen. Now, if I look at my balanced chemical equation, 2 moles of oxygen produces 1 mole of carbon dioxide. So how much carbon dioxide would I produce from all that? I would have half. And my answer is 0.875 moles of CO2. Who is my limiting reagent? Who produces less carbon dioxide? This guy right here, right? That's how much CO2 I could produce in this reaction. CH4, therefore, is your limiting reagent, and O2 is your excess reagent. There's way too much oxygen there. There's going to be some that's left over. Still didn't answer the question, though. The question is asking what volume of CO2 is produced at 2.50 atmospheres and 1.25 or 125 degrees Celsius. Now that I know that I would produce 0.189 moles of CO2, I'm actually going to use PV equals nRT again. But in this case, I'm going to solve for volume because that's what I'm trying to find. I know that I want this final product to have a pressure of 2.50 atmospheres. I'm going to solve for V because I want to know what the volume is. I'm producing, based on that limiting and excess reagent problem, 0.189 moles of CO2 R, and T would be 398 Kelvin. You would have a final answer of 2.47 liters. This is a lot, okay? You have to really understand the process. Why did we do each of these things? College boards, a lot of times, will not directly ask you what is the limiting and excess reagent, especially in a multiple choice question. You have to be able to identify the limiting and excess reagent just by being given a problem like this. 2 scenarios, 2 gases. Here's their information. How much product can be formed? You have to know that it's limiting and excess reagent problem. It takes a lot of practice, right? I hope to give us as many practice problems as I can with this. That was a good one. That's a good problem right there. Let's finish this off talking about good old Dalton, right? So Dalton's law of partial pressures, and we're going to talk more about this in class because this one is important. It seems very simple, but and I'm going to add a little bit of something to this that I think you really need to know. But anyway, what am I doing? Here we go. Okay, let's get the colors that we like. Dalton's law of partial pressure says that the total pressure of a mixture of gases is equal to sum of the individual partial pressures of the component gases. So what does this look like? So equation looks a little something like this. PT, where T is the total, right? So T is the total. The total pressure in a system is equal to the sum of all the constituent gases. And this number goes on because this could be equal to, if there's 50 gases that make up a sample, the sum of all 50 gases. You're not going to have 50. 3 or 4 is usually the max. So what does this mean? Here's some gas. We'll call this gas A. Gas A is in this first tank. Okay, this tank all has some volume. We could see here that all of these have the same volume. They're the same size. So same V. This gas exerts a pressure of 300 kilopascals. So these gases are bouncing off the walls of the container and exert a pressure of 300 kilopascals. Gas B, little bit more moles of gases in this container. So because there's more moles of gases in the container, these particles bounce off the walls of the container more frequently. Therefore, they exert a higher pressure. Whereas this last one right here exerts a pressure of 450 kilopascals. And now that I'm looking at this, this doesn't make any sense. Why would that be 450 when this is 600 and this looks like it has more particles in it. I don't like that at all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. This should technically have 26, right? 1, 2, 3, 4, 5, 6. There's definitely not 26 there. I think they switched these up. This looks like this should be 450. And this looks like this should be 600. Huh. Nope, don't like that example anymore. But anyway, that's besides the point. Let's just pretend. This one also exerts some force on the sides of the container. If I were to take all 3 of these gases and pump them into another container that has the same volume, the pressure, the total pressure would be equal to the sum of all of these, 300, 600, and 450. In here, however, we still say that the partial pressures are the same. The partial pressure of gas A still exerts a pressure of 300 kilopascals, right? And that's because A is still bouncing off of the walls of the container with the same amount of force. Granted, the total pressure is greater, because when you combine all 3 of those gases, they put a much stronger force in the walls of the container. But A is exerting the same force throughout, because I didn't add more moles of that gas. So that's what we call the partial pressure. A still exerts the same partial pressure. Same as B. B still exerts the same partial pressure, 600 kilopascals. And that's because these are all at the same exact volume. What we can also do, and I think this one is most important, and I wish I had it in my notes, but I don't, is we can determine what is the partial pressure of a gas just by looking at the mole ratio. So if we consider, and this is a terrible example because of course the one with the most particles is not the highest pressure, it's fine. The partial pressure that is going to be the highest is the one that contains the highest number of moles of gases. And that's because they're colliding with the container walls more often. So if I wanted to find what's the partial pressure of gas A, if I wanted to know, if I was given this right here, and I wanted to know what's the partial pressure of gas A, you could figure that out by taking the total pressure and multiplying that by the number of moles of A over the total number of moles. This is basically giving us a percentage. So what percentage of that particular canister is A? And if it's 30%, right? 30% of the total would give me the partial pressure of just that individual gas. We're going to practice this in class quite a bit too, because I see lots of multiple choice questions like that. And I tend to forget to use this law. So I am really going to focus on that with you, because if I'm going to forget to use it, then you're definitely going to forget to use it. So I think we need to practice that as a class so we all become more comfortable. Like I've told you before, I'm still growing in my chemistry knowledge. I'm finding gaps in what I teach to you, so I have to make sure that I fill those gaps, right? And here's one gap in particular that I think we need to talk about in class more, is especially Dalton's law. That's all that I'm going to cover for gases for this particular unit. I do have that independent study video that you can also watch, but we're going to do lots of gas law practice stuff in class. There's no, I can't tell you how to solve every single gas law question because there are so many different gas law problems. It's crazy. So the only way to get good is just to practice, and that's what we're going to do in class for the next little bit. As always, if you have any questions, please let me know, write down any notes, come and see me in class, and I will see you in the last video for this unit, which should be very short and simple, which is all about solutions. I will see you then. Bye.